Sir,
Please, anyone reply.
addition reaction and substitution reactions.
Sorry, pardon me.
Sir, good morning, sir.
Ah,
Addition reaction and substitutions reaction.
addition reactions and substitution, both.
Substitution.
Only substitution. Aromatic compounds, however, it is having unsaturation in it is undergoing substitution rather than the addition. That is the only criteria when we observe the reactivity. Aromatic compounds, that is, just I am going to define here the ability of is monocyclic or simply anything. I'm not giving the Huckel definition. Just in generalized, I will giving a cyclic conjugated system to undergo substitution reactions. Substitution reactions. What are the substitution reactions? The substitution reactions may be electrophilic, that is, the reaction is initiated by the electrophile, or a nucleophilic, to taken as evidence for the taken as evidence for the aromaticity of aromaticity of a aromatic compound of a aromatic compound. For example, I'm going to take the reaction of you are already done during the experiment. Annealing. When you subject it to the bromination, simply it is need to undergo the addition reaction on unsaturated system. But however it is unsaturated system, it is undergoing substitution reaction that leads to produce what is the product? You are already synthesized during the practical sessions. What is this product? Tribromo.
1, 2, 4 tribromo aniline.
Yes, 2, 4, 6 tribromo aniline. Now, when you cleanly observe this reaction, suppose the same bromination, if I am going to conduct on this one, or a simple double bond, if it is undergoing reaction with the two molecules of bromine, then it leads to formation of tetrabromo butane. On the same olefin, it gives dibromo olefin, dibromo alkene. Okay, these are the due to the nature of aromaticity, it is undergoing substitution reaction. This is the substitution reaction. But in these two cases, when you observe these two cases, these two are the addition reaction. Now, simply we can recognize that when we compare the unsaturated compounds, whether they are the aromatic or olefinic in nature. If it is olefinic in nature, that is undergoing the addition reaction. If it is in aromatic in nature, it is undergoing substitution reaction. Now, second one, resonance energy. Resonance energy. in this resonance energy. I already discussed what is the resonance energy. Okay, all the aromatic compounds are associated with the resonance energy. That may be a positive energy or negative energy. Okay, all the unsaturated is simply called as all the conjugated polyene system, whether it is a cyclic or acyclic, whatever it may be, all are having resonance energy. When resonance energy is shown, if it is arranged into different resonance structures, then it is associated with resonance energy. When we come into aromatic compounds, this resonance energy is the important phenomena to explain the aromaticity. Because when you take the aromatic compound and its corresponding acyclic polyene system or its corresponding 4 and 5 electron system, when you compare these three, aromatic system is having the positive resonance energy. When you take the simple acyclic olefin, it is having the zero resonance energy. When you take the 4 and 5 electron system, polyene system containing the negative resonance energy. Okay, this based on these three factors, we can understand the what is aromatic, what is not aromatic, or non-aromatic, and what is anti-aromatic. Okay, but when you coming to the aromatic compounds, these are having positive resonance energy. All organic compounds are associated with the resonance energy. What is the responsible for the resonance energy? What is the responsible for the resonance energy in the aromatic compounds? The responsible thing is delocalization of 5 electrons. Delocalization of 5 electrons. Suppose here you take the benzene. Well, simply you can represent this benzene in two Kekulé structures. Two Kekulé structures. This is one Kekulé structure, and this is another Kekulé structure. Kekulé structure 1 and Kekulé structure 2. These are the who are the resonance structures. When it's generalized structure, that is the both are the cyclohexatriene structures. Okay, when we represent these two resonance structure, we believe it hypothetically believed as benzene. Hypothetically, these two are believed as benzene. But when we are considering the exact resonance structure, exact structure of benzene is like this. That means whatever the three double bonds are there, what are the 5 electrons of these three double bonds are in the delocalization manner. Due to this delocalization, the system energy becomes decreases. When system energy is decreases, when we comparing the stability of this resonance hybrid and resonance structure, when we have the different value of energy, okay, it is having some higher energy, it is having some lower energy. When detect this value, suppose it is having the X, it is having the stability energy. When X minus Y will get the positive resonance energy. Positive resonance energy. Now, when it is showing a positive resonance energy, that is aromatic. This positive energy, resonance energy is responsible by the delocalization of these 5 electrons. Please remember that. Okay, and aromatic substances is more stable than the most stable resonance structures. Resonance hybrid. Here, the resonance hybrid is given. The resonance hybrid is more stable than the resonance structures. Resonance hybrid is always more stable than the resonance structure. Okay, resonance energy is the difference between the stability of resonance hybrid and the most stable resonance structure. Whatever we are taking here. These are the thing. Okay. Next, how this experimentally the resonance energy can be determined. How the resonance energy can be determined. That thing. Yesterday I have given that some example, that is the benzene is taken, that is based on heat of hydrogenation, data, and heat of combustion. Yes, someone is send a message. Okay. Heat of combustion. Are you feeling bored? I'm going slow, very, because some slow learners are there during practical session. I understand that most of them are slow learners instead of fast learners. Actually, in the PG level, most of them are fast learners are there, but in this group, most of them are slow learners. That's why I'm going slow. Is there any problem? If you can ask me, I will speed up. Right. Now, yesterday we had already discussed the heat of hydrogenation, where I am going to, I have taken the values of energies in the form of kilojoules per mole. Here I am going to explain the kilocalories first. Okay. Heat of hydrogenation method. Calculation of resonance energy using heat of hydrogenation. First one. Heat of hydrogenation data. Now, in this reaction, in this method, what is that? We simply take the formula. The resonance energy is equal to calculated calculated energy of hydrogenation hydrogenation minus hydrogenation of the compound. This compound is what? Hypothetical compound. Why I'm saying this is a hypothetical compound? Just for benzene, we are considering cyclohexatriene is the model structure. Now, minus experimental heat of hydrogenation of the aromatic compound. This is the original compound, aromatic compound, that the original substance we are taken, and that we are subjected to heat of hydrogenation calculation by experimental. Now, this is the formula we are using for this. For example, I am considering the benzene, because it is very most popular. Its data is already available in the literature. That's why everyone is taking this benzene. For the benzene, for calculating resonance energy, I am taking the cyclohexene is the model structure. On hydrogenation, we are using some catalyst that like nickel, nickel, like that. Right? On hydrogenation, it leads to produce the cyclohexene. Then it evolves 28.6 kilocalories per mole on heat of hydrogenation. That means the heat is evolved during the hydrogenation. Therefore, for one double bond, heat of hydrogenation requires 28.6 kilocalories per mole. And for a hypothetical one, that is the cyclohexatriene for benzene alternative structure. That means for three double bonds of heat of hydrogenation, how much amount it takes? Into 28.6. That is equal to 85.8 kilocalories per mole. right? This is the value. For benzene, experimentally, these are the theoretical values. First, we are conducting the one experiment. Based on that, we are calculated the for three development. This is the theoretical, theoretical or hypothetical calculation. Calculation, right? For experimental, I just take the benzene. This is the benzene present in hybrid I am considering. On heat of hydrogenation, again I am conducting heat of hydrogenation, hydrogenation reaction in presence of catalyst. Then this also leads to evolve the heat that is equal to 49.8 kilocalories per mole. Right. Now coming to the resonance energy. Based on the above equation, above formula, resonance energy is equal to theoretical value or calculated value. Calculated value is what? What is the calculated value? This one. Calculated or theoretical or hypothetical value. That is 85.8 minus experimental value. What is that? 49.8. That is equal to 36 kilo calories per mole. Okay, similarly, this one is the positive resonance energy. That is the positive resonance energy. We observe the positive resonance, once we are observing the positive resonance, it is aromatic. Okay, clearly indicates that the compound is aromatic. That is the criteria is successfully executed. Next, coming to heat of combustion. Heat of combustion is also similar way. Heat of combustion. From the heat of combustion data, uh, just a minute. No, when you are conducting the combustion reaction on దహనోష్ణం అంటారు in Telugu. Okay, just we are heating to in pyrolytic conditions. Now it leads to ash and it releases to that 275.03 kilocalories. Kilocalories. Now, similarly, from this is the experimental value actually. Actually, this is the experimental value. When theoretically or calculated, theoretically, we calculate the combustion of the cyclohexatriene, how much amount is released, which is just heating at pyrolysis condition, it gives the ash. Now it gives the energy 8 to 25. This is a calculated one. How it is for three double bonds, 3 into 275.03. That is equal to 825.1 kilocalorie. Right. This is the experimental or theoretical, sorry, calculated or theoretical. When you can take the same benzene, its resonance hybrid, just conduct the combustion, then it gives to ash. Now it releases the energy 789.1 kilocalories. Then what is the resonance energy of benzene? Resonance energy of benzene equal to 825.1 minus 7 89.1. How much is remained? 36 kilocalories per mole. Now the resonance energy is positive again. Positive resonance energy. Therefore, it clearly proven that benzene is aromatic, right? Based on the heat of hydrogenation and heat of combustion. But this criterion is not always satisfactory. This criteria, what is that criteria? Heat of hydrogenation and heat of combustion or heat of other thing. You can take any thermodynamical phenomena. Those are not always perfectly gives the accurate results. Therefore, this criteria is not always satisfactory. Since a choice of suitable model, why in this case, benzene case, we can select the cyclohexene is available. From that, we are calculating the values for the cyclohexatriene, a suitable model for the benzene. It is available for benzene. That's why we have calculated. But in all the cases, this kind of model may not be available because it is not always possible due to large ring sizes with steric interactions and many possible conformations. Whenever the number of carbons are increases, the ring sizes are becomes increases. Due to that reason, the corresponding models may not be available, and due to the increasing size, steric interactions or repulsions are takes place. Physical phenomena will affect on the structure. Therefore, it will leads to the formation of a non-planar conformational structures. Due to that reason, we are unable to calculate an accurate resonance energies for that molecule. Okay. In the case of benzene, it is possible because we have well we have the available of structure cyclohexene is available, and from that we are going to we have calculated from the cyclohexane to cyclohexatriene heat of hydrogenation and heat of combustion values. Okay, therefore it is the limited application. This criteria is the limited application. Now coming to heat of bond lengths and planarity. It is very important aspect for deciding the aromaticity. For deciding the aromaticity, it is very important aspect. An aromatic molecule must be sufficiently planar to allow the extensive overlap of pi orbitals in such a way that a perfect delocalization will take place. Suppose if the structure is not in planar, there is no perfect overlapping of pi orbitals will not takes place. There is no perfect overlapping of pi orbitals will be observed. Therefore, delocalization is not maximum extent. Delocalization is not maximum extent. Therefore, the aromatic property, that means in such a way that this is not happen. What a maximum overlapping of pi orbitals, or extensive overlapping of orbitals, and a perfect pi electron delocalizations are absent, then there is a possibility to different bond lengths are observed in the within the cycle, within the ring. Due to that reason, it lasts the aromatic property. Therefore, the mandatory criteria is it should be planar. Then only it is planar. We can observe that homogeneous bond lengths and homogeneous bond angles between the carbon-carbon in the ring system. Therefore, in aromatic molecules, all the CC bond lengths of the systems are equal or nearly equal. If when you come into this is they happen in the aromatic cases. When you come into the non-aromatic molecules are non-planar, and the CC bond lengths of the pi system are alternatively long. That is, this long bond is single bond, alternatively long and alternatively short. Whatever the short bond, it is due to the CC double bond. Alternation is more frequently observed in the non-planar structures. Once we are observing the non-planarity in the molecule of conjugated polyene system that is not eligible to study under aromatics. Please recognize it. It can also determine by the it can also determine the bond lengths and bond angles by using the X-ray analysis of molecule. It gives the information regarding the bond lengths and bond angles and its planarity. Okay, this is the important criteria to know the bond lengths, bond angles. Based on that, we can decide whether it is the planar or not. Then it satisfies all the conditions. That means it should be a planar. Then only when it is planar, delocalization, d orbitals overlapping is in maximum extent. Once the d orbital becomes maximum extent, it should be a planar. Therefore, it satisfies the aromatic property. Then followed with other criteria, right? For example, here yesterday also I have given the example, same examples I am repeating here. When you take the benzene at the any when you take the benzene, you observe that this is the benzene. Now, this CC bond length, this CC bond length is 1.4 angstroms. At any case, it is 1.4 angstrom, it 1.4 angstrom. That all 6 carbons are connected, the bonds are 1.4 angstroms. 1.4 angstrom, and here also 1. Right. But in the case of cyclooctatetraene, it is a non-planar. At any time you observe that cyclooctatetraene tetraene is exist in the tub shape. This one. There is a double bond here. There is a double bond here, and one double bond is here, and another double bond is here. Next, the bond length here it is 1.35 angstroms. Here also 1.35 angstroms. Right. These single bonds 1.5 actually 53 angstroms. It is 1.53 angstroms. Simply can take one decimals 1.5 angstroms, 1.5 angstrom. Now here this double bond is also 1.35 and 1.35 angstroms. That means wherever the double bond is there, that is having the bond length is 1.35 angstroms. Wherever the single bond is there, that shows the 1.5 angstroms. There is a alternate bond lengths where somewhere it is short, somewhere it is long. Where the long is that is responsible for the single bond, where the short is the responsible for double bond, right? Next to an aromatic molecule, in some aromatic molecule, even if all the CC bond lengths are not identical, at least it is the this criteria sometimes fail. Some exceptions. Some exceptions. These are the general criteria. But when we are observing the exceptions, what are the exceptions in the case of anulines? In the case of anulines, like 18 anulin, I am giving here. I am going to give here. This is the 18 anulin. Okay, this is the 18 anulin. Due to some slippery in my writing pad, that's why I'm not able to give the exact bond lengths. Okay, right. In the aniline, these are hydrogens are called as intra-annular hydrogen bonds. Intra-annular hydrogen bonds. Uh, hydrogen, intraannular hydrogen, not hydrogen bonds, intraannular hydrogens. And these hydrogens are known as extraannular hydrogens. Actually, this is the 18 only. It is aromatic. It is aromatic. But exceptional thing in this is it shows the alternate double bonds. It shows the, as per the Hückel rule, it follows the Hückel rule, therefore it is aromatic. But when you observe the structural features of this molecule, it is showing alternate bonds. This is the 18 already. How these alternate hydrogen bonds are shown, I will show you here. I'll take yes, look at here. Wherever the block means a thick line, this is known as transide double bond. So transide bond. It is a double bond actually. Transide bond. It is a shorter one. That means it is a double bond. And the second one, whatever the thing bond we are representing in red line, that indicates the cis-oid bond. Cis-oid bond. That is a longer bond actually. Longer bond that indicates the single bond. This is the double bond. This is a single bond. Okay. Why these kind of alternates are observed, we cannot explain in some aromatic molecule, even if all the CC bond lengths are not identical, at least the alteration is not observed. In some cases, alteration is not observed, but 18 alanine, it shows the aromaticity. But whenever we are studying the X-ray crystallography studies on this molecule, it shows the alternate double bonds. Okay. Next, whatever the next one. Yes, diamagnetic ring. This is the important, next, last, and most important aspect. Diamagnetic ring. Right? Diamagnetic ring current. In the NMR spectrum, so I actually saw Mohan sir started yesterday. H1 and MR spectra. Okay. In that H1 and MR spectrum, some factors will influence the chemical shift value. Some factors which are influences the chemical shift value. What are the factors? Most probably electronegativity, electronegativity, strength of magnetic field, strength of magnetic field. Right. Third one is an important phenomenon, anisotropic effect. Anisotropic effect. Anisotropic effect. Right. What is this anisotropic effect? What is the anisotropic effect? Suppose not only NMR, we can see the proton NMR. In the C13 NMR also, H1 NMR or in C13 NMR. In both the cases, if a molecule is subjected to NMR magnetic field, suppose this is the magnetic field, These are the bar magnetics. Whenever you are keeping the molecule in the form of a tube, right? Whatever the protons or carbons present in the molecule, some of them are aligned or are parallel to the magnetic field, and some are opposing the magnetic field. Some of them are opposing the magnetic field, some of them are parallel to the magnetic field, right? Whatever the parallel the which are aligned to parallel, which is aligned as parallel to the magnetic field, those are called as paramagnetic atoms. Like if it is hydrogen, paramagnetic protons and paramagnetic carbons. Suppose hydrogens which are opposing to the magnetic field, those are called diamagnetic, right? If it is proton, diamagnetic protons or diamagnetic carbons. Then similarly, here also, if the benzene is like this, it is having six hydrogens, six hydrogens. Now, whatever this molecule is under magnetic field, all the protons fall in paramagnetic region. That means parallel to the magnetic field. Like this. The magnetic field I'm showing clearly here how the magnetic waves will influence on the this is the alignment of molecule in the magnetic field. Yes, this is the resonance cloud or pi electron cloud. Yes, when you are applying the magnetic field in this direction, in this direction, this is the applied magnetic field, right? Now, this applied magnetic field, whenever we are applied magnetic field, some magnetic force are opposing the magnetic force which are generated by the molecule is opposing this magnetic field. This is called a diamagnetic region. These are opposing. Okay, all the protons which fall on the magnetic field and which are aligned to the parallel to the magnetic field, all protons. Whatever the pi electron cloud is there, that pi electron cloud is opposing the magnetic field. Therefore, this is the diamagnetic region. Diamagnetic region. This is the region, paramagnetic region. Once they are falling to the paramagnetic field region, they will be precise. Their precision frequencies are high. Precision frequencies are high. Therefore, that will be gives the peak at a higher precision frequency value. That is higher chemical shift values. Okay, that is called off field. That is called sorry. These are having high chemical shift values. High chemical shift values, then the corresponding olefins. This is called de-shielded protons. These protons are called de-shielded de-shielded hydrogens. Suppose any hydrogens are falling diamagnetic protons. This is called low chemical shift, low chemical shift or shielded protons. Shielded hydrogens are shielded protons. Therefore, it is having the low chemical shift values. Low chemical shift values. Chemical shift values. Okay. Now, whatever the region, that is the high tau values, For example, in the graphical representation, I am writing a graph. It is a TMS. Then it is starting from 0. Now it is moving on left from right to left. Its value becomes increase. Suppose it is a 10 delta. It is the 0 delta, right? Now, when you take these below, these values are minus delta values. When you move on, this is the 10 tau value, 0 delta or 10 tau. When it is the 10 delta, it is the 0 tau. That value is, this is below, and the above value is called minus tau value. Now this is called low field or D shield. D shield. This is high field or shielded area. Okay, high field and D shield. Shielded or D shielded or low field or high field. Okay. Now aromatic systems are associated with the diamagnetic ring current. When a magnetic field is applied, that is called applied magnetic field. It is applied to perpendicular to this way. Applied to perpendicular way to aromatic ring. The pi electrons are induced. These pi electrons are induced to circulate and produce the magnetic field. Whenever we are applying the magnetic field, this pi electron cloud will be induced to produce an opposing magnetic field, or it produces a magnetic field. And sometimes it may be opposing, it may be parallel. Okay, that is called induced magnetic field. The induced magnetic field opposes the applied magnetic field. This is known as diamagnetic ring current. Suppose this pi electron cloud, my cursor is moving, my cursor is appearing. Can you see the cursor? Are you seeing the cursor, please? Please tell me.
Yes, sir.
Okay, right. This, whatever the pi electron cloud is there, that is aligned to opposite to the applied magnetic field. Then it produces the induced magnetic field. That induced magnetic field is known as diamagnetic ring current. The opposing magnetic field is called, opposing induced magnetic field is called diamagnetic ring current. When this diamagnetic ring current, due to the diamagnetic ring current, in aromatic molecules, peripheral or extraannular hydrogens are de-shielded. In previous case, what are peripherals, what are the extraannular? Previous aniline, I have given that example. In the aniline system, you see that these hydrogens are called extraannular or peripheral. These are found in the de-shielded area. Therefore, they are observing low field, that means the low tau values, or high field, higher delta values in the NMR spectrum. These are the peripheral or external protons are fall into the de-shielded area or low field area. Therefore, they show the lower delta value. Lower delta value, that means the lower values of tau values and higher values of delta values. Right? These are called extraannular or peripheral. Whatever the inside protons, all the 6 hydrogens, these are called what we call it as intraannular or inner hydrogens. Intraannular or interhydrogens. Internal, we call it as internal hydrogens. Internal hydrogens. Okay. Now, in aromatic molecules containing annular hydrogens, these are also simply called as annular hydrogens or These inner hydrogens are internal hydrogens or shielded. Why it is shielded? These are fall in the diamagnetic region. They are opposing the applied magnetic field. Therefore, their resonance values appear in the spectrum, NMR spectrum is high field, that is the lower delta values, lower delta values, and higher tau values, higher tau values, right? These are called diamagnetic protons. These are diamagnetic protons. That's why it is getting the lower delta value. These are the paramagnetic protons. These are getting the higher delta. Okay. In this way, we can observe that when you come into the aromatic compounds, whatever the protons which are fall in the paramagnetic or whatever the extraannular or peripheral proton which are fall in parallel to the magnetic field, or it is having a positive diamagnetic ring current or de-shielded and therefore absorb lower field values, that is the higher delta values and lower tau values, and the aromatic protons which are containing annular hydrogens which are fall in the diamagnetic field, therefore they will be shielded and extra they will produce they fall into the shielded area, and due to that reason, they shows the lower delta values or higher tau values. Okay, these are the simple phenomena to explain the compounds aromatic. Due to the diamagnetic ring current in benzene hydrogens, peripheral hydrogens are de-shielded and observed in lower fields of H1NMR spectrum. Okay, this is the thing you need to understand. This is the diamagnetic ring current will affect the protons of the aromatic substances. In non-aromatic molecules, if it is aromatic molecules, this thing is happening. What is that? In the aromatic compounds, extra-annular or peripheral protons are fall into the de-shielded area. They may therefore they gives the higher delta values or lower tau values, and the inner protons or annular protons are fall into the diamagnetic current, therefore diamagnetic region, therefore they will be shielded. Due to that reason, they shows the lower delta values and higher tau values. But this scenario will be different in the case of non-aromatic and anti-aromatic compounds. In aromatic molecules, the protons observed in the olefinic region, there is no change. It is the unsaturated one, non-aromatic. We are not considered that molecule is is not a aromatic. That is the reason we simply those molecules are showing the delta values or tau values. The molecules of olefins which we are showing in that region, these non-aromatic molecule protons can show the peaks. Next, in the case of anti-aromatic systems, the annular protons are de-shielded. It is quite opposite to the aromatic system, in the anti-aromatic and the aromatic. Simply, its name also influence it. Simply, it is opposite. Whatever the annular protons or inner protons or intra-annular protons will fall into the paramagnetic region, they will be persisted at a higher precisional frequency value. Therefore, it gives the peak at a higher delta value or lower tau value. That is what is the reason? It is de-shielded. Due to that reason, they are appearing in the lower field value, and whatever the extraannular protons or peripheral protons are there, they will be shielded. Why it is shielded? It is fall in the diamagnetic region, therefore they are shielded, therefore they fall into the shielded area or shielded field. Now, or high field, they fall into the high field. They shows the lower delta values and higher tau values. For explaining this phenomena, I will give you a table here, the H1NMR data of some molecules, H1NMR of some aniline molecules, of some aniline molecules. If you take the compound, chemical shift.
Sir,
Ah,
sir, one doubt, sir.
Yeah, yes, ask us.
The protons which are falling in the paramagnetic regions,
Hmm.
they are parallel to the applied magnetic field, sir.
Why here when you are any object, you are applied the or you are putting in the magnetic field.
Sure,
You imagine that if any object is put into the any magnetic field,
sure,
some part of the object will be exactly aligned to the magnetic field. Some part is opposing, correct?
sure,
Some part is opposing.
sure,
When you are taking the molecule in similar way, it is put into the applied magnetic field. In the molecule is also some part is actually aligned to the parallel to the magnetic lines or magnetic field. Some part is opposing the magnetic field,
sure,
right?
sure,
Whenever we are after applying the magnetic field, the
sure,
molecule containing atoms, actually hydrogens, the
sure,
hydrogen, we are concerned with the HO number. These hydrogen or these protons will be undergoing the precision. Precision means when you are imagine the a top, what we call top, we are playing tops, you know that.
sure,
Playing tops, you know that. Okay, when you round the thread and just throw it, it will be circulating. That is called precision.
sure,
Okay, how it is showing the precision? It is aligned to the magnetic field of Earth with a 0 degrees angle.
okay,
Whenever you are using the top, you are playing with the top. The top will be circulated at vertical. It is stand and circulated. That is called 0 degrees angle precision. That is the example for precision. Similar way, in the atom containing, sorry, molecule containing hydrogen or hydrogens or protons will undergo such kind of precision with some angle, with some angle. When you are applying the magnetic field, there is a change in that angle. Further, some of them are opposing the magnetic field, some of them are
sure,
aligning to the magnetic field.
sure,
Right. Whatever the protons which are aligned to the magnetic field, whatever the protons which are aligned to the magnetic field, just please wait. Laptop battery is some low. I will connect the batteries, please. Yes. Now, similarly, whenever we are putting the object in the magnetic field, some part is aligned to the magnetic field, some part is opposing the magnetic field.
sure,
Similarly, the molecule having the protons, some protons are aligned to the magnet, that is arranged to parallel to the magnetic field. That concept is called paramagnetism. Some part is opposing the magnetic field, that is called diamagnetism or diamagnetic field paramagnetic. That means the molecule is split into paramagnetic field and diamagnetic field. Whatever the protons which are fall in the paramagnetic field, the precision frequency, so it is having some frequency after parallel to the applied magnetic field, their precision will be increases. It rotates very fastly. Okay. Therefore, whenever the object is rotating very much fast, to control the speed, we need to apply some energy. Suppose you take the two tops. One top is moving very fast. One top is rotating very fast. One top is rotating slowly. Okay, we are not clearly observed, but if you are observed that for stopping the top speed or top velocity is more, we are applying some more energy. The top is moving slowly. That is to stop the top, we are applying lower energy. Similarly, whenever it is rotating, it come to resonance. For resonance, we are applying RF value, radio frequency. That whatever the radio frequency we are observing, we are applying the top precision and the radio frequency comes resonance. That means the radio frequency and the top rotating frequency both will be matching. That is called resonance. When they becomes the resonance, that will gives the peak in the H1 number. Okay. Both will be coming into the resonance. It requires the high frequency radio frequency. If it is slow, it requires the low frequency RF value. Okay. There is a difference in the observing the RF value. The proton which is having the high velocity, it takes the higher frequency radio wave. If the proton is having the lower precisional frequency, it is slowly rotating, then it requires the lower energy radio wave. Okay, this is the phenomena to show the peaks in the H1NMR spectrum. Okay, whatever the protons which are fall in the paramagnetic region, they are rotating very fast. Whatever the protons which are fall in the diamagnetic region, they are opposing the magnetic field. Therefore, the rotation will be decreases. Therefore, they rotate slowly. Due to the difference in this velocities of rotation, the radio frequency wave consumption is different to get the resonance. Therefore, here the whatever the protons which are fall in the paramagnetic region, it gets the peak at a higher delta value or lower tau value, right? Or the diamagnetic proton which are comes to the resonance at the lower frequency. Therefore, these are comes shows the peak at a lower delta value or higher tau value. Whatever the protons which are having the higher precisions. Therefore, there is no shielding. There is no screen to stop the rotation of that proton. Therefore, that is called de-shielded protons. Those de-shielded protons will be appear at a higher frequency value, higher delta value. The shielded protons, that means the protons are opposing the magnetic field. There will be their rotation will be shielded. Their rotation will be blocked. Due to that reason, those protons will appear at a lower frequency values. In the aromatic compound, which we are applied to which we are placed in the extramagnetic field or applied magnetic field in the NMR spectrum, though some protons are fall in the paramagnetic region, some protons are fall in the diamagnetic region. Based on that, we'll get the delta value. Based on the delta value, we can decide whether it is aromatic or not. Once you see this table, we can clearly understand. Okay? Can
Yes.
you
Thank you,
did you
sir.
get the answer?
Sir. Thank you, sir.
Yes. It is only possible when you are understanding the principle of H1NMR, not only H1NMR, NMR spectrum principle. Then only you can easily understand annular hydrogens. Annular hydrogens will in internal protons. Hydrogens, ring current, aromaticity, aromaticity. Okay. These are the extraannular protons. These are intraannular protons. Two different types. Suppose benzene, you take the C6H6. In this case, there is no intraannular protons. And what is the generally seen the proton values at the delta is 6 hydrogens are showing the same value at the 7.3 delta. Now, the ring current is diamagnetic ring current. Due to the diamagnetic ring current, the protons are fall in the paramagnetic region, the pi electron cloud fall in the diamagnetic region. Okay, this is the diamagnetic ring current. Diamagnetic. Therefore, the aromaticity nature is aromatic in nature. Aromatic. Similarly, cyclooctatetraene. Cyclooctatetraene. It is having 8 protons. These 8 protons are showing the same value but lower value. It is nearly equal to the whatever the olefin presents, olefin shows. 5.69 delta. 5.69 delta. There is no annular protons in this. Extraannular protons are the extraannular protons. It shows the delta value is 5.69. And actually, there is no ring current because there is no delocalization. The delocalization pi electron cloud will not fall into anything. Therefore, it is non-aromatic. Because it is non-planar actually. In the top shape, it is stable. Non-aromatic. 10 annually. 10 annually. That means all the 10 hydrogens are extraannular protons. All the 10 protons are extraannular. It will show the delta value from the range 5.62, 662, 5.84 delta. There is no annular protons. Now, this is also the 10 annular system. It is non-planar. That is the reason there is no ring current. It is also non-aromatic. Non-aromatic. It is non-planar due to the design non-aromatic. Next, 12 annular. 12 annuline. In this 12 annuline, it is having 9 hydrogens of the extraannular protons. Total 12 hydrogens are there, but in that 9 of them are the extraannular protons. This will show 5.652, 6.22 in the range, delta range. And annular protons, that is intraannular protons, it is having 3 protons. It shows 9.07 delta. Now, the ring current is paramagnetic. Delocalization is there, but it is the paramagnetic. Paramagnetic. Therefore, it is anti-aromatic. Anti-aromatic. Next, 14 annuline. 14 annuline. In that 14, 10 hydrogens fall in extraannular and remaining 4 hydrogens fall in annular protons. Actually, all the protons of 10 hydrogens are falling in higher delta value, 7.6 delta. And this will be shows there is no precision frequency. Exact the magnetic field and its frequency both becomes equal. Therefore, there is no precision frequency. There is no delta value for this. Therefore, the ring current is diamagnetic. Diamagnetic. Therefore, it is aromatic. This is aromatic. Right. Next, similarly, 16 only. Up to this, we will discuss up to 22 only. 22 only. Uh, First, 16 only. It is in the out of 16, 12 hydrogens fall in extraannular. Therefore, it shows the 5.4. Next, in the case of 16 only, 4 hydrogens fall in the annular protons. That is 10.43. The ring current is paramagnetic. This is the anti-aromatic. Anti-aromatic. Right. Next, you take the 18 only. And out of the 18, 12 protons are the extraannular protons, and that is 9.28. And remaining 6 hydrogens, you look at here. high, high field. That means 2.99 minus value, minus delta value. Observe minus delta value, but the ring current is diamagnetic. It is aromatic. Aromatic, 1800. Next, 20th angle. 20th angle, 20 angle. In the out of 20, 13 hydrogens are fall into the extraannular protons. That is 4.12, 4.12, 6.6. And remaining 7 hydrogens, these are fall into the annular protons. That means 10.9 to 13.9 delta. Here the current is paramagnetic. This is anti-aromatic. Next, 22, second one. 22 only. 8.52, 9.65. Out of 22, 14 hydrogens are fall into extraannular, and 8 hydrogens fall in annular system. That is the minus 0.4 to 1.2 delta. This is also diamagnetic ring. It shows the diamagnetic ring current. This is aromatic. Okay. I will share the material the same. You can read it. Okay. We have several examples are there. So from smaller molecule to up to 24 aniline. Some of them are aromatic, some of them non-aromatic, some of them anti-aromatic. I will share that material. Okay. Now we have the important topics. Two topics are remaining in this unit. One is the explanation, that is the postulates of Huckel rule and the limitations of Huckel rule, Prost-Muslin diagrams, and the classification of aromatic compounds into benzenoid, non-benzenoid, alternate and non-alternate. And another rule is we have Cram's rule is there. These four concepts are remaining. We'll discuss tomorrow, next class. Okay. Thank you.
Thank you.
Thank you, sir.
Okay.
Thank you, sir. Thank you, sir.
Sir, sir, excuse me.
చెప్పండి చెప్పండి అండి.
Class tomorrow will be at same time.
Actually, only Saturday, Sundays classes.
Okay, okay. So next class you will cover.
In the Saturday, next class will be.
Ji, sir. Thank you, sir.
Right.
Good day, sir. Good day, sir.
Thank you, sir.
Okay, I'm closing the session. You'll join to next session by 1:30 to 3 o'clock in physical chemistry class.
Okay, thank you, sir.
Okay, sir. Okay, sir.